Hi and welcome to my video on an application to antidifferentiation, which is kinematics. And let's be honest, we're going to start calling it integration. Now this comes from the Mathematical Methods course. It is Unit 3, Topic 3, and it follows on from an introduction to antidifferentiation. So there's some learning goals, success criteria, have a read of that, my expectations, and now let's move on. So you know about integration, and here is an application. I won't go through my attempt to be funny there. But we do know already from our work with differentiation that if you have a displacement model and you derive that with respect to time, remember our displacement model will be position with respect to time. So you derive that function with respect to time, you'll get velocity. And you derive velocity with respect to time, you get acceleration. So we've seen that in topic 2 of Unit 3 and also in Unit 2. Here's something new though, and maybe you already knew it. If you want to go back up the chain, we just need to integrate with respect to time. So you can see in the light blue there that we've integrated to get from acceleration to velocity with respect to time. You've integrated to get from velocity to displacement with respect to time. Now you may already be thinking, well, that causes a problem because we end up with this pesky constant, this c value. We don't know anything about this c value, and that's true, definitely true. But if we know something about the velocity and something about the displacement, which often we do, usually we know the initial velocity or the initial displacement, then we can easily calculate the c value and work out a particular or an exact velocity and displacement function. So integrate to move back up. Don't forget though, it has to be with respect to time, and known velocities and displacements can help eliminate constants. So I've just got a couple of examples for you and then I'll leave you with it. So example 1, which looks a bit like a doozy, but this is a common type of question in the exam. It is really real. It is motion under acceleration. It's the most common one that we deal with as humans on this earth. And so I'll give you this example. You don't need to have a physics background. You don't need to have all this knowledge. You just need to know how to integrate to be able to work a question like this. It's got 6 parts, but you really want a question like this in your exam because there are easy marks within this. But also, if you don't know how to do the first couple of parts, you will lose a lot of marks. So let's start with part A. And I'll do this in a different color just so we can see where I've worked. What is the ball's initial velocity and displacement? A ball is dropped from a 10-meter high platform. If a ball is dropped, it means it doesn't have an initial velocity. Now, we do have to deal with that velocity directionally, so we have to make sure that we're careful to take a negative and positive value. But here's the ball. It's dropped from a platform, so I think we can assume that it's been dropped over the edge of the platform, and it begins to travel down under the influence of gravity. But it doesn't start moving up. It doesn't start with any velocity. So we've got v naught, that's our way of writing the initial velocity, is equal to 0 meters per second. And of course, then we have the displacement. So what is the initial displacement here? Well, the initial displacement is that this platform is 10 meters high. So this thing is 10 meters off the ground. So x naught, well, I'm using x for displacement, could be s, could be d, although d is avoided because we don't really like a dd to t statement, but x is 10 meters. It's really important to recognize and be able to pull out your initial values, and part A may not exist, but you need to still be able to remember to do it. Part B, what is the function for velocity in terms of time? Well, we know acceleration. Acceleration is equal to negative 10 meters per second squared. So velocity is equal to the integral of acceleration with respect to time, as we've already determined. And that means that velocity is equal to the integral of negative 10 with respect to time, which is negative 10 t plus some constant. Now, we know that at t equals 0, v equals 0. So we can substitute those both in, and it gives us, everything cancels out, it gives us c is 0, and so therefore velocity is equal to negative 10t. The velocity at any point is negative 10 times the amount of time that's passed to get to that point from where the ball was dropped. So that's a good start, and it's negative because obviously the velocity is heading down. Part C. What is the function? What is the function's displacement in terms of time? So the displacement x is equal to the integral of velocity with respect to time. In this case, that's the integral of negative 10t with respect to time, which is negative 5t squared plus some constant. Now, it's really important to be careful here. Realistically, in an external exam, or probably an internal one even, you wouldn't lose any marks. But mathematically, I've used C already. So what I'm actually going to start doing, and hopefully you might pick up, is I'm going to call that one C1 and that one C2. You have to just make that C1. And that way I'm just not double dipping on my constant definition. So I get this. At t equals 10, x equals, sorry, my apologies, at t equals 0, x is equal to 10. So I've got my initial value, and I can put that in now. I get 10 is equal to negative 5 times 0 squared plus C2, which means C2 is equal to 10. And so if C2 is equal to 10, then x is equal to negative 5t squared plus 10. So there's my displacement model. Question D. How far does the ball travel in 1 second? Well, the ball at 0 seconds hasn't travelled at all. So in 1 second, all we have to do is substitute in t equals 1, and we get x is equal to negative 5 times 1 squared plus 10, which in this case is negative 5 times, that is negative 5 plus 10, which is equal to 5. Now this is going to be a little bit confusing and double dipping, just because of the way I've written this example. But remember, the ball started at 10 and it finishes at 5, so it's travelled 5 meters. And it's a coincidence that we got 5 here and it's travelled 5 meters. If we had got, for example, and this is wrong, so I'll do it in red, let's say we got 6 meters there, then this would be 6 and this would be 4. So you just got to be careful you translate that into the problem space. The other thing you have to be careful of is if this ball was thrown up, so let's say it starts at a 10 meter platform, it's thrown up and then comes back down, and that's 1 second there, well, it may have travelled this bit up and then this bit back down, and you'll need to work out the total amount of distance travelled. But that's a difference between displacement and distance. So distance being how far it's travelled in total, which we don't use as much anymore. Usually we care more about position. Where is the ball now? How far away is it? And that, in that case, how far away is it? It's just that direct distance. So if we had a how far away is it question, we'd be dealing more with just the overall difference. So just be careful with some of the wording and how you approach some of those questions. Question E. How does when does the ball hit the ground? So let's have a look. We have a lack of space. We have our x model, negative 5t squared plus 10, and we want to know what is the value of t at x equals 0, because it hits the ground when x equals 0. So we put x equals 0 in, negative 5t squared plus 10. That gives us negative 10, or actually no, a better way would be to add 5t squared. So 5t squared equals 10. Divide by 5, we get t squared is equal to 2. And we get t is equal to, and be very careful you don't forget that it's equal to plus or minus 2, which is plus or minus 1.414, something like that, the square root of 2. Okay, and this is obviously in seconds. Now, this is a contextual problem. So we have this minus value here. It doesn't really make sense to have a negative value. And that just represents the fact that the ball is at a 10 meter platform initially, and it drops down, but the model starts at 0 and starts to increase down. If you filled in a complete quadratic, it would look like this, and that would be your minus answer. So it just comes from the theoretical fact that that quadratic goes on forever, but contextually we start at time equals 0 and all times have to be positive. And question F, what is the ball's velocity when it hits the ground? Well, I know that it hits the ground at t equals root 2, and I also know that the velocity is equal to negative 10 times t, which equals negative 10 times root 2, which equals, well, approximately negative 14.14 meters per second. So it's traveling down at 14.14 meters per second. And there's the answer to question F. So keep in mind, you'll see some of these in the textbook, that if you get a question that looks like it's got a million parts, well, that just means it's a normal question scaffolded, and it's probably worth 10 marks or something, and that is a great moment for you.